It is well known that the building industry is the largest carbon emitting industry today. And some of the key reasons are that they are made with materials with high embodied carbon, constructed in a process of discrete assemblies, and designed in an analytical but top down manner. And in this project, we not only want to propose solutions to these issues, but provoke a radically alternative possibility. We believe that the buildings of our future are living entities, biologically alive, physically intelligent, and ecologically regenerative. And the only questions are, what will it be made of, how will it be grown, and what will be its form? We are trying to answer these questions by driving research and innovation in three separate frontiers simultaneously: biochemical engineering, robotic fabrication, and digital computation, and creating an integrated transdisciplinary system that can enable us to design living buildings. The three research agendas have three separate outputs. The first is an engineered living material. The inspiration for the engineered living material comes from stromatolites, which are naturally growing biomineralized rock-like formations made by photosynthetic cyanobacteria communities. And it is known that the process of biomineralization in these stromatolites is linked to the production of extracellular carbonic anhydrase that catalyzes the precipitation of calcium carbonate. But the biggest challenge was that in nature they grow one microbiofilm layer at a time and therefore takes hundreds of years to grow. We therefore hypothesized an alternative process based on tissue engineering techniques. We tested the growth of cyanobacteria in a range of different hydrogel compositions that are typically used as scaffolds for growing artificial tissues. And a significant breakthrough was made by devising a composition that allowed the cyanobacteria biofilm to grow in a three-dimensional matrix. By using appropriate aggregates and nutrient media, we were able to grow a translucent biomineralized living material within a span of weeks. We have tested this material under ambient conditions and have found the biofilm to be viable even after a period of 180 days. This means that this living material is regenerative and photosynthetically active. And preliminary data shows that it can sequester around 1000 ppm of CO2 over a 28-day growth period. At the same time, this material is hardened by biogenic calcium carbonate and has a capacity of 6 to 7 megapascals, which is similar to the compressive strength of a conventional brick. We then tested various scale-up production methods of this material. First, by digitally generating a mold and casting the ELM top-down, but also a bottom-up process of growing the ELM naturally, photogrammetrically reconstructing and modifying it based on the application scenario, and robotically carving the material into a desired shape. Simultaneously, we developed Python-based custom computer vision programs to evaluate its growth, monitor its health, and extract relevant data for design and application. Finally, we were able to successfully grow a large 1:1 scale architectural panel of size 2 feet by 1 feet within a period of just 6 weeks. This novel translucent engineered living material therefore presents the opportunity of a new regenerative biomineralized carbon negative architecture. However, to truly arrive at a living architectural structure, we require a whole system of intelligent biomaterial fabrication, which is presented in the next chapter.
So how can we fabricate an environmentally informed multi-material structure that enables growth through its performativity? And how can we integrate biofabrication parameters straight from the design stage? To achieve this, we need to shift the way we operate on a material, software, and a hardware level. On a material level, 3 biocomposites with reversible responses to water have been developed. Material A has a shape memory response, and together with material B, the ELM, they change from translucent to transparent, whereas material C is non-responsive and serves as a structural composite. All consistencies have been adjusted for robotic extrusion. These composites introduce varying performative qualities regarding strength, light filtration, and water containment. These qualities trigger different biological responses across the structure's volume. On a software level, we developed a customized design and fabrication workflow. Initially, a generation of prints which have fabrication constraints integrated in their genes is created. Then the selected outcome undergoes fab-led optimization and maxillization. This allows for efficient solar radiation and solar heat gain analysis to be conducted. The resulting data are imported into a machine learning algorithm to define the material's distribution, and the material-informed toolpath is generated. Material interlace was tested in multiple ways, vertically, horizontally, and diagonally. All three methods were successful in the upscale, with the vertical interlace to have the best performance. On a hardware level, there is the downside of programming a performance based only on data libraries, which holds the risk of failure upon exposure to live conditions. Therefore, material distribution is updated during printing by a real-time feedback system comprised of a temperature and humidity sensor. Once there is a mismatch between the predicted and the existing values, the air supply changes between cartridges to extrude the most suitable material. Condition statements driven by material properties are guiding this selection and ensure that not the same material is printed for a long period of steady conditions. We propose a dynamic fabrication process which generates automated but not identical outputs. We can now predict but do not predetermine. With the help of the developed workflow, we can apply this agile process to multiple scales. And usually this would have been the end, but we envision a continuous process where the finalized piece is evaluated by a camera attached to the robotic arm, which scans it and detects cracks and failures. In areas where the cracking is severe, ELM is extruded to act as a biobinder. The scanning is repeated regularly throughout the structure's lifespan, and the collected image data are fed back into the system to serve as criteria for the next iterations of the evolutionary algorithm. The same toolpath can create 1,000 outputs. One output will have 1,000 faces.
The first computation challenge is to create a site-specific and context-aware emergent algorithm to generate architecture. Therefore, we developed an intelligent agent-based swarm system. Its neighbor sensing behavior is driven by the radiation data. To generate architecture spaces, the swarms were subjected to a vortex force to create cylindrical habitable spaces. As multiple axes applied with different directions, architecture spaces are generated. The next attempt is to assign a repellence logic to the swarm. Searching radius and repellence force led to various porosity. The locations of the repellence points are then defined by certain environmental matters. This characteristic informs the scale of space. To test the performance of the swarm trails projected on complex curvature surfaces, a series of platonic solids are tested with fibrosity. It textualizes the morphology of the swarm system and deducts the way repellence logic happening in 3D space. The next challenge is to inform the swarm system with biology and fabrication aspects. We assign the swarm system with material identities by extracting the actual texture data of the various materials, then test it with both PBR and procedural material visualization to translate biomateriality into architectural quality. This indicates a potential for a type of living architecture that has a gradient of softness, transparency, and a dynamic responsiveness to environmental factors. by using quaternion rotation displacement. This data-driven mode in generative progress encounters the geological force and is fully programmable. The emergent surface geometry undergoes annual solar exposure analysis. The produced data guide the aggregation deformation. Denser patterns are generated around areas of huge exposure to protect living cells. The final challenge was to use multi-material gradation to create desired spaces for a new spiritual experience. The walls arose from the ground as a biomineralized photosynthetic skeleton. This skeleton was integrated with an environmentally functionally graded material exoskeleton. This EFGM is intelligently guided by solar radiation data and functionally transports nutrients and moisture to the living walls. At the same time forms fibrous architectural fenestrations and roofs. It is translucent, multi-material, and is photosynthesizing, playing with light and moisture, encouraging biodiversity, creating a novel experience of nature and technology. It brings a new era of integrated bionic habitat for humanity.